Good morning from Dhaka, Bangladesh. This is the 12th lecture of AS and A-level chemistry lecture series. I'll discuss shapes of molecules in this lecture. I have shown this slide in the last lecture, but didn't clearly explain it. Therefore, I bring it again. So, how to predict shapes of molecules? There are 2 points we have to take into account. We have to find out number of pairs of electrons around the central atoms, and also how many lone pairs of electrons and bond pairs of electrons are there in the central atom. If we want to do that, we need to draw the Lewis dot structure of the compound or ion and find out number of bond pair and lone pair, and then predict the shapes of molecules. You know, pair of electrons, these are negatively charged, and therefore they will repel each other. And once we get the pair of electrons, we will have to get the electron pairs will have to have apart from each other so that it has got repulsive force minimized. Once it gets repulsive force minimized, we can predict or draw the shapes of the molecules. An example, now I talk about valential electron repulsion theory. This theory says the lone pair repulsion will be the highest, and then lone pair bond pair repulsion, and then bond pair repulsion. Therefore, we will have molecules with bond pair as well as with lone pairs. And this example, methane, you can see that this is the central atom, that is carbon atoms, and it is bonded with hydrogen atom, hydrogen atom, hydrogen atom, and hydrogen atoms. So we are getting one pair of electron here to bonded with hydrogen atom. Similarly, this pair, similarly this pair, and similarly this pair. And then these 4 pairs of electrons would be arranged in space so that their repulsive force are minimized. And once we arrange like this, then we say that the angle between this hydrogen atom, carbon atom, and hydrogen atom, 109.4 degree. Once we get a shape like 109.5 degree, we call this a tetrahedral shape. Now, I am going to next slide, and it could say that we could have number of electron pairs here, that number of electron pairs, and then arrangement of these electron pairs, which dictates us for the shape, and then what is the shape and the predicted bond angle. With the predicted bond angle, we name the shape. So if we have 2 bond pair, and we have to have minimized bond pair repulsion, and we see that that will have a bond angle 180 degree, and therefore this shape is linear. Similarly, if we have 3 bond pair, we go and we have seen that this is an angle 120 degree, and shape will be then trigonal planar shape. I talked about the tetrahedral shape a few minutes ago, and then we go for if it is 5 pair of electrons, and if all of the pair of electrons are bond pairs, then we get the shape trigonal bipyramidal, and the angle between this one will be 90 degree, and the angle in the plane will be 120 degree. So such a shape we call trigonal bipyramidal. Now we go for 6 pairs of electrons, and if all are the bond pair, then we get an octahedral shaped molecule. The angle between this and in the plane are 90 degree. So it becomes an octahedral shaped molecule. Next slide is, you see, we don't get only bond pair in molecules or ions. We do have also lone pairs. That means this lone pair of lone pair are not bonded. That's what we call lone pair electron. And as you remember that we said valential electron pair repulsion theory, the bond pair will have least repulsion, then bond pair, lone pair, and then lone pair, lone pair. So we have a lone pair and bond pair here in ammonia. Therefore, the shape will not be anymore, though it is 4 electron pair, but the shape will not be as 4 bond pair. It will be a distorted one. And therefore, we see that nitrogen, hydrogen, and nitrogen, hydrogen, the angle becomes 107 degrees. So this is a case of one lone pair. Similarly, we could have some molecule having 2 bond pair and 2 lone pair. This is the one, and water is this example of that. If we draw the Lewis structure of water, we will see that there are 2 bond pairs and 2 lone pairs. And in that case, oxygen, hydrogen, and oxygen and hydrogen, the bond angle becomes 104 degree, 4.5 degree. So we cannot call, though it is 4 electron pairs, because of 2 lone pairs, the shapes distorted. Well, we have been talking till now all bond pair molecules, did not include any lone pair. So when we draw the Lewis structure of ammonia, we'll see that there is 1 lone pair in it. If we draw the Lewis structure of water, we will see that there are 2 lone pairs. Lone pairs are shown like this, lone pairs. So when we have a lone pair and bond pair in a molecule, we will have bond pair repulsion as well as bond pair lone pair repulsion. When we have 2 lone pair in a molecule, we will have bond pair lone pair repulsion and as well as lone pair repulsion. So when it is a lone pair repulsion, we get greatest repulsion between lone pairs. And when it is a bond pair repulsion, it is least repulsion between bond pairs. And when it is a bond pair and lone pair, 1 lone pair, then it is intermediate repulsion. Due to this lone pairs repulsions, the original shape becomes distorted. So if we would have 4 bond pair, we would have a shape. And then if we include a lone pair in it, the shape becomes distorted. If we include 2 lone pairs, the shape becomes still distorted. So we take this, and here one thing to be shown. This nitrogen and hydrogen and this nitrogen and hydrogen are in one plane, same plane. But this nitrogen and hydrogen are not in same plane. So therefore, we are showing it in a black dot arrow. Okay, we go to the next slide. Here I have taken consideration of lone pair, bond pair, etc. So if we have an electron system, 2 electron system, that is 2 pairs of electron, we do not have a lone pair in it, and we will not have lone pair, because if we have only 1 bond pair, we cannot have a shape. We have to have minimum 2 bond pair to get the shape. So in this case, we have 2 pairs of electrons and both are bond pair, and we have a shape like this, and we call it linear shape because angle between these 2 bond pair is 180 degrees. An example is carbon dioxide. If we draw the structure of carbon dioxide, you will see that there are 2 bond pair. There are the 2 bond pair. If we go for the number of electron pair 3, and if all the 3 are bond pair, then this is bond pair, this is bond pair, this is bond pair, then we call it trigonal planar shape, which I said in last slides. And here there are no lone pair, therefore we have the shape like this, and the angle between these two becomes 120 degrees. But then in this system, we could have possibilities of 2 bond pair, 1 lone pair. And here this is the 2 bond pair, this 2 bond pair, this is lone pair. And due to this, we get the shape not trigonal planar, it becomes a band shaped molecule. And example is nitrate ion. Nitrate ion, remember that. And then we go for 4 pair of electrons. We have talked about methane, where there are only 4 bond pair, no lone pair, and therefore we have a shape like this, and we call it, if you remember, that this is a methane, and there is in one, this hydrogen is one plane, and these two are above and below. And the shape is called tetrahedral shape. Now we have the possibilities of, in this system, 3 bond pair, 1 lone pair. If we have 3 bond pair and 1 lone pair, it was, if you remember, example was ammonia, and here is ammonia molecule with a lone pair, and that shape now we call it trigonal pyramidal. And the angle, if you remember, is 107 degree. Nitrogen, hydrogen angle is 107 degree. Now we are having another system in this system that is 2 bond pair, 2 lone pair. We talked about it in water molecule, showed it, and that is these 2 are lone pair, and therefore this is the bond pair, and their angle now becomes 104 degree. In the shape we call it band shape. We have the next one is 5 pair system. If it is only bond pair, we say this is a trigonal bipyramidal molecule, and an example is phosphorus pentachloride. If you draw the Lewis structure, you can see there are 5 bond pairs. This 5 bond pair, this is in the plane, and this is above the plane, below the plane, and call it trigonal bipyramidal shape. Now, in this system, we can have 4 bond pair, 1 lone pair, 3 bond pair, 2 lone pair, 2 bond pair, 3 lone pair. And we could have shape like this. One is called seesaw shape with 1 lone pair and 4 bond pair. And then 2 lone pair and 3 bond pair, T-shaped molecule. And then this one is a linear molecule, because bond pair are lone pairs are not shown in the shape. So this is a linear molecule. Next slide is with a system where we are discussing about 6 electron pair. And the shape of 6 bond pair by only bond pair, we discussed it in other slide, that it's an octahedral shape molecule. So whenever we have a lone pair, the shape becomes distorted. So if we have 5 bond pair and 1 lone pair, this is a distorted octahedral shape, also called square pyramidal shape. Here again, 4 bond pair, 2 lone pair. This is distorted octahedral shape, or also called square planar shape. Examples are sulfur hexafluoride, bromine trifluoride, xenon tetrafluoride. There are a few more things in shapes of molecules. Here we see we have been talking about water and methane, ammonia. These models, these are called space-filling models of methane. This is space-filling model of ammonia. Here we see we have a lone pair, and this is space-filling model of water. These are bond pair, and this is lone pair. This is oxygen, this is hydrogen, this is hydrogen. This is ammonia, this is carbon, and this is hydrogen. We not only can predict the shape of molecules, we can also predict the shape of ions. I have taken few examples of ions here. Hydronium ion and bromine, boron tetrafluoride, and amine ion, and also show the shapes of those. And this is pyramidal shape. This is tetrahedral shape. This is band shape molecule. And this one, we have a double bond here in the central atom. And here also in carbon double bond in the central atom. So double bond and triple bond are also treated as only a single bond, and the shapes are accordingly named. So here, double bond, single bond, treated as single bond. Therefore, it is a linear. And here, trigonal and planar, and this one is tetrahedral bonds. Well, we go to the next slide, that is giant covalent structure. Some nonmetals, such as carbon and silicon, they do have a very strong structure, though they are covalent bonds. So molecules having covalent bonds and simple covalent bonds, they are with low melting point and they are not strongly bonded as ionic bond, but a few nonmetals, as I said, like carbon and silicon, they have giant structure. These structures are having very strong and they have high melting point. Similarly, some compounds of nonmetals, silicon dioxide, boron nitride, they exist also a giant covalent structure. As I said, well, about allotropes, an element which has different structural form in the same physical states are called allotrope. So, for example, carbon has got diamond structure, graphite structure, different fluorine structure, and graphene structure. And all of these are allotropes of carbon. They have also, some of them have also giant structure. We talk about, let's say, silicon dioxide. One can see here, this is silicon, and it is bonded with 4 oxygen, giving an tetrahedral shapes, and throughout 3-dimensionally, it is arranged like this. And therefore, silicon dioxide is a giant covalent structure. Similarly, diamond has got giant covalent structure. One of this is a carbon, and this carbon is bonded with 4 other carbons and forming 3-dimensional structure, and becomes very hard and strong structure, though these are non-metals. So next structure shows some of the allotropes of carbon, that is graphite. If you remember, we are talking about close packing, layers of close packing. And this is the carbon atom bonded with 3 other carbon atoms, and they form a layer. And these layer and these layer are again bonded, and this layer and these layer are again bonded. If we look to it, this layer, if we call this one A, the other layer is B, then you see the third layer is exactly A. So it is an A, B structure. If you remember, we call it hexagonal close packing structure. So similarly, if we go for fullerene, you see here, this is the carbon atoms and bonded with other 3 carbon atoms, and like a ball, it structures like a ball. It's a C60. Its composition is C60. It's also called buckyball structure. And then we have a graphene structure. You see, this is a simple graphene structure. It's an allotrope of carbon. Professor Andre Gein and Kostya Novosel isolated this and solved the structure of a single layer graphene in 2003 and got Nobel Prize in Physics in 2010. Well, so far we have been discussing structure and bonding. We can see that if we know the structure and bonding, we can predict the physical properties, or if we know the physical properties, we can also predict the structure and bonding of the covalent molecules. This is all about the bonding and structure of A-level syllabus. In the next lecture, we'll talk about redox. What is redox? Reduction and oxidation. The reaction, oxidation reactions and reduction reactions. These are very important reactions, and it is in A-level syllabus, basics of redox reaction. I will talk in the next lecture. Thank you very much for today's lecture.